Okay, so I use the word ionosphere because that's still part of what you might call our heliophysics world. But in actual fact, what I'm really going to talk about is a lot to do with the atmosphere in which the ionosphere exists. And it's that atmospheric part which perhaps when we talk about exoplanets, we can envisage that the exoplanets have atmospheres. And what does space weather do to that atmosphere? And of course, one of the things is it creates an ionosphere. So that's the kind of linkage that I'm targeting. So it's in two parts this morning. We'll have a break at some point. So needless to say, there's a ton of material out there about ionospheres, and even in our heliophysics summer school textbooks. The Tim Fuller-Rowell in Volume 1 has a kind of nice ionosphere thermosphere chapter. Stan Solomon in the third volume, chapter 13, has more on the thermosphere side of things. And then there's a textbook, Shunk and Nagy, that isn't lying up there, oddly enough, but it talks very definitely about ionospheres, including planetary ionospheres, in great detail. And of course, Dana has already done an excellent job in introducing you to an ionosphere in the primary physics. Okay, so some of what you're going to hear today will be repetition, but I think that's good. How many of you are not ionospheric physicists? Yeah. Okay. So for you guys, this is excellent. Good for you. Yeah. Okay. So the takeaway message from this talk would be an appreciation of how important a narrow ionospheric layer in our atmosphere is for various heliophysics space weather processes. A narrow layer. In fact, Michael showed an equivalent one on the sun in a neutral atmosphere getting very hot. And we'll see similarities with very similar type processes. So this layer has different names. And the name SARE we're going to define a little bit later in this talk. But we have an E layer. It could be called the E layer. It could be called the turbopause. It's also where the Pedersen and Hall conductivity layer is. And from an MHD point of view and current closures in the ionosphere, that is particularly important. So magnetospheric physics comes in. And the altitude range for our terrestrial world is between 100 and 120 kilometers. So that's what we hope you'll take away. And down here, well, Michael's 5-minute talk preempted this nicely and showed exactly such a layer, the transition layer, where the temperature just skyrockets, density goes down. Okay, so with that in mind, I had a question for you right away, and of course, Michael answered that very clearly. How many of you before this week realized the sun had a neutral atmosphere? One, a half. Okay, but that's a huge takeaway message in solar physics. There is a rather huge amount of neutral gas that goes into all kinds of processes for kind of plasma physics. It's really important. Okay, so that's where we are. The neutral atmosphere. All ionospheres exist in an atmosphere, okay? The thermosphere-ionosphere forms the neutral to plasma interface between planets with atmospheres and space. So that's kind of our kind of a line, if you like, this 100 to 120 kilometers. And we're going to explore it a little bit further. Oops, oh, sorry, let's back up for a second. The composition of the ionosphere is governed by the atmosphere itself, the chemistry that's ongoing, and of course this ionizing radiation. And we'll see that the chemistry leads to different species that are uncommon in the lower atmosphere. One more, sorry. The atmospheric dynamic influences the ionosphere. So the atmospheric dynamics, we even heard a young speaker talk about tides and other phenomena being generated low down, propagating up. And during this period of very quiet solar activity, that term, if you like, that driver force is even more apparent than it would have been 20 or 30 years ago when we had lots of activity. So apart from photons, what other forms of ionizing radiation are there? That's a question. Quick. What else ionizes? What other? Pardon? energetic particles, such as electrons, protons. Okay. Right, and we're going to come to that in the second half of the talk. But to begin with, we're talking about photons. Okay, so here is a very typical example you must have seen. Pardon? Oh, meteors. Okay, that's getting more in depth than I was expecting. Yes, let's not have too many of these big ones. Okay. What we have here is simply the typical species that one thinks of. There are other ones, argon and other examples that we could throw into this, but O is the one that's kind of special and neat. It doesn't exist in our lower atmosphere in any reasonable amount. It's a chemistry-generated species. O2 and N2, of course, are the ones that form our air. We know the ratio, and we'll talk about that in a second. Okay, so that's where we start. And this one figure generated from a model of the neutral atmosphere called EMSIS pretty much gives us a first insight as to how space solar cycle works. Here's your 100 to 120 region. There are 4 traces drawn on here, and each trace represents the temperature of what we'd call the neutral atmosphere at these altitudes. Down here, it's all kind of one temperature. And what we've got are 4 traces. So we've got solar minimum is the main, winter, summer, midnight, noon. And then we've got solar maximum, winter, summer, midnight, noon. So these are the extreme conditions, if you like, for solar illumination during a solar cycle. So at noon, solar maximum, it has this kind of temperature above this region that we've talked about, and it's at 1600 Kelvin, if you like. At night, the temperature drops significantly, and at solar minimum, the range, of course, is even lower. But down here, our kind of normal atmosphere temperature is only about 300 Kelvin. There's a minimum in the mesosphere, and then it increases depending on the solar cycle conditions. So there you have what you might call how is the atmosphere driven by the solar cycle, the changes in what's going to be the EU flux. And you can see this dynamic range of almost a factor of 3. But lower down, there is no effect. This little difference that you see below 100 is actually in the mesosphere. It's a winter-summer circulation problem that is responsible for this. The summer temperatures are lower than the winter ones because of this transport process. Okay, so that's our first hint, that this 100 to 120 is a demarcation between space and our hard planet's atmosphere. You can see that also. These temperatures then change the scale height of the neutral gas above you, and of course that leads to a density change. So satellites in low Earth orbit between maybe 300 and 500 do experience different amounts of drag depending on the solar cycle. But lower down here, the densities are relatively unaffected by this kind of solar cycle. Okay, so again, 100 to 120 kilometers. Another way of talking about this is from the pure way in which the gases mix or are not mixing. So lower atmosphere has turbulent mixing, which leads to a constant composition. So when we talk about the oxygen to nitrogen, we all have a number like 80% is nitrogen molecules, 20% is oxygen molecules. This is true all the way up to about this 120 kilometers. Above that, they go into above the turbopause. This is called the turbopause under these conditions. It goes into their own hydrostatic equilibrium. Okay, so again, there's a demarcation band with a slightly different name this time. And the thermosphere is the region above, which is responding to the solar cycle, and below is what's called the mesosphere. Okay, so another kind of attribute of the separation region is the generation of atomic oxygen. Here on this plot, the concentration of molecular oxygen and molecular nitrogen. As you come up through altitude, again into this region, above this, the neutral O is being generated. And as you come down below this, the mechanism is kind of, how shall we say, becoming minimal, if you like. So this chemistry, if you like, low down here is very ineffective. But as you come up into the kind of region that we're, the transition region, the oxygen, atomic oxygen is being created. Okay, so of course you've already heard about this too, that the neutral atmospheres on both Venus and Mars are referred to as terrestrial type atmospheres. Their composition isn't quite terrestrial. What's the big difference between Mars and Venus and us? What's the dominant species in the atmosphere at these altitudes? CO2. And I'll put the other one up too. Here's Venus. Again, CO2. And you can see again the chemistry that's ongoing generates oxygen, atomic oxygen, through chemistry. Okay, so we have the similar kind of conditions, and we'll eventually see that there is this boundary region on these planets as well, but we'll get there. Okay, so the other aspect of CO2 and nitric oxide in our case is they're phenomenally good radiators of energy. So as solar energy through EUV and soft X-rays comes into this region and gets absorbed, the presence of CO2 on these planets and nitric oxide being generated in the Earth's atmosphere actually is a very important part of the energy budget. They radiate in infrared and dump heat back out into the universe, if you like, at these higher altitudes. Okay. So we'll now turn around and see what these atmospheres do in terms of under ionizing conditions. They produce ionospheres, and we'll talk about that. The first thing is we needed that neutral gas to get the ionosphere. Then the next thing is, even though we call it an ionosphere, and one thinks of a plasma as a very dominant component, in actual fact, the neutral gas is still enormous. So the plasma component, if you like, is only a few percent or a fraction of a percent of the total number density. It's collisionally rich. Most of the time constants at these altitudes are very fast. Minutes, tens of minutes. Some of the species can live longer. Okay, the EUV then is, and you've heard about this, and the soft X-rays. Under quiescent normal conditions, the solar EUV, and we should throw in Lyman alpha, a little bit longer wavelength, are very important. The difference between daytime and nighttime, of course, nighttime you understand that the sun isn't exactly shining. It's gone away temporarily. But at night, we do have a resonantly scattered sunlight. So, for example, Lyman alpha scatters resonantly from the hydrogen gas that's surrounding the Earth and generates some residual ionization. Starlight most certainly generates a little, as well as the cosmic ray ionization. So at night, things don't just stop, but the level of ionization is much lower. Then, of course, these are the photons, but one also realizes in certain parts of the Earth, especially the polar regions, high latitudes, you do get other particles being generated that lead to ionization, and we'll talk about these later. And then the other little part of this is the region that we are looking at where all this ionization occurs in the neutral gas leads to electrical conductivity. So again, I'm kind of leading you down this path. If you had to guess at what altitudes are these conductivity channels? Does anybody want to guess where I'm driving you to? What altitude is the conductivity channels in the ionosphere? Sorry, this is not meant to be rocket science. I'm leading you down a path. Where is this? What's this altitude going to be? Okay, 100 to 120 kilometers. You're going to find that all of these different processes we're talking about are anchored And this then becomes a rather easy separation between space and the atmosphere below. Okay? Okay, so here we go. This then would be what we ionospheric people would regard as a very reasonable day-side profile of the electron density. So it's the electron density, it's a solid line, and the suggestion is it's made up of 3 populations. And in our case, we have these very light ions, helium and hydrogen, at the higher altitudes, above 800 to 1,000 kilometers. Low down, we have moleculars that are dominant, the molecular ions. And, of course, in between the region, we have this oxygen, O+, as the dominant ion. So our kind of ionosphere has been labeled historically as a D, an E, an F1, and an F2, kind of representing, to some extent, peaks, if you like. It turns out that from the observational point of view, using an ionosonde, these little cusps, if you like, show up very clearly in an ionogram. And that led to them being called E and F1 and F2. But in actual fact, when you kind of model this structure, there aren't necessarily peaks. There are kind of inflections in the shape. And the only real peak that's almost always there is what's called the F2 layer, where the oxygen ions are dominant. Now, the D region, if this gets more complicated with molecular ions being generated, down here, you even have negative ion chemistry. Most of us think of ions as being positive, electrons stripped off. But in actual fact, down in the D region, it gets even more complicated. Molecules can actually have attachment, and they're negative ions. Okay, so we're not going to go down here. And this is our 100 to 120. It looks like there's no more ionosphere beneath us, but there is still a residual ionosphere. Okay, so just to break us up for a second, how many of you have GPS? Okay, how many have used it that weekend in your mountain climbing? Okay, so how bad can your GPS become in terms of accuracy? So bad. Okay, you've got to switch it on first, of course. Okay, so so bad. What do you think? Okay, if you're driving a car with your eyes shut, what's the likelihood of staying on the road? Okay, so here's our kind of question. Our GPS system, especially if you're just using a very simple system, the L1 or something, or L2, then your GPS accuracy is determined by what's called the total electron content from the ground to the GPS satellite. And the majority of that comes from this region here. The F layer is what's generating. What does it do? You've got all these electrons. How do they affect your geolocation? What's the process? So you've got radio waves coming through the upper ionosphere, through the neutral atmosphere to your receiver. What's the process that's going on? Why this is so important? A time delay. It's a refractive index problem. Basically, the more electrons you have in here, the more retardation or slowing down of the signals. And that way, you've got multiple paths to different GPS satellites, and they're all being contaminated through different parts of the ionosphere. So inhomogeneities in this spatial distribution from one latitude to the next, from one local time to the next, leads in these simple systems to GPS inaccuracies. Does anybody have a number? How many centimeters, meters, kilometers can that error be? No? Okay, it's meters to tens of meters under extreme conditions. Okay, so that's why we care about the ionosphere. That's why you care about the ionosphere too. Okay, this is the O+. The chemistry occurs deep down in the collisional region, but the other part of the F region is this diffusive equilibrium. We've got a nice temperature structure and the distribution of the O+ ions. With gravity, of course, being vertical, there is a diffusion process. And we end up with, normally it's termed diffusive equilibrium, but during geomagnetic storms, it's never in diffusive equilibrium. But it's a combination low down of chemistry processes, recombination and production, and a higher up, the diffusion comes into the equation. Unfortunately, this little schematic, perhaps it's slightly hard to read, but basically the photons most certainly come in and generate from the neutrals the first level of our ions, moleculars, atomic, and generate species like the O generates O, and it also generates NO, the neutral NO. So there are actual species in the neutral gas that are generated through this photochemistry. The other really important thing is the photoelectrons that are generated are now slightly energetic. They're not at the thermal energy level of the 1000 Kelvin of the neutral gas. They are much more energetic. And that energy can either lead to further ionization or in the thermalizing, we're going to end up with the electron gas being hotter than the neutral gas. And we'll see that later. Okay, we're familiar with the word reaction rates, whether you're on the sun or elsewhere. But are these constants? If you write down an equation for a particular reaction rate, is the reaction rate constant? What does it depend on? Temperature, good. I mean, that's the primary thing. And that makes this entire problem very complicated during storms. If you're dumping in a lot of heat, the temperature of the gas around us is changing, and the reaction rates are different. So that leads to large modifications in what you would call the standard ionospheric distribution or profile. Okay, well, Mars has an ionosphere. And remember, CO2 was the dominant neutral in the region that we were kind of talking about, this lower region. And higher up we had O+, neutral O being created. And what we end up with is a very rich molecular O2+ major ion. And the O2+ being a molecule, on the Earth, this peak would be normally termed an E region peak rather than the F region peak. On the Earth, the O+ is our dominant ion most of the time, and it's called the F region peak. So the slight difference might be that the dominant ion is a molecule on Mars. And Venus is the same, although the Venus data sets aren't quite as rich. They go back many more years. But nonetheless, the mass spectrometers have most certainly found a similarity, the O+ at high altitudes and the O2+ lower down. And again, one would call this an E region, and this kind of lacks a distinctive peak, but this would be the F region. Okay, so photoionization, the solar EUV irradiance is key. Only recently has the short wavelength component become routinely observable. Now, what we mean by that is our solar spectrum, the EUV that we're familiar with, that goes from maybe 10 nanometers up to maybe 120 nanometers, we include Lyman alpha, do most of the ionizing in what is that solar cycle dependence that we put up at the beginning. The neutral atmospheric temperature above 120 kilometers varies from solar minimum night from about 800 Kelvin all the way up to 1800 Kelvin. So that that's primarily done by the EUV. The soft X-rays, or the short wavelengths, are the soft X-rays, 1 to 10 nanometers. And they're special, and we're going to talk about them a lot more. They're mainly associated with flares. As we heard today again, that the flares generate very large increases in the locally received irradiance for soft X-rays. So the kind of well, I should just say that our field still lacks a good way of describing the storm variability, the flare variability of that soft X-ray component. There's a number of attempts to model it with proxy indices, but we're still, I would say, not doing a good job. The satellite databases have been awesome. The Time-C, with its one great spectrum per orbit, and then the SDO with its EVE instrument, generated with very high time cadence, resolving time cadence for flares, what the Earth was receiving. Okay, so we're kind of reasonably well covered for the EUV, but not so for the flares yet. Okay, this is not meant to be read. Can you read that at the back? Now, when you build a computer model that takes just the photoionization processes and tries to get closure, you've got all the processes. This is the kind of block diagram you would end up with. The kind of photoionization, it seems pretty straightforward. We get that, and this is the 10 to 120 nanometers, which is well-defined part of the spectrum. You plug that in and you get ionization. For most of these photoelectrons, there's not enough energy to produce further ionization. So these generate, if you like, thermal heating in addition to ionization. But then at the other side of this diagram, when you have these soft X-rays, which one or two nanometers, it's almost 1,000 electron volts. The typical number we would use as a rule of thumb is you need 34 electron volts to create another ionization. So a photoelectron at 34 eV can generate one more ionization. If it's 340 eV, the rule of thumb, if you like, would be 10 further ionizations. So soft X-rays are very important because if you increase their flux, as we'll hear, by three orders of magnitude, the effectiveness of these very short wavelength but energetic photons is enormous, and the secondary ionizations are really important. Okay, and down here, the consequences of all this is basically energy absorption. We get the neutral gas being heated, the ions are heated, and the electron gas is, of course, heated. So the combination of all this includes the energy equation. And as we said earlier, the energy equation not only changes the temperature, but the reaction rates are changing. So during a big storm, this kind of process, although it's just photons and neutrals, it gets very complicated. And as I said earlier, NO, and in the case of the two terrestrial planets, Mars and Venus, the molecules NO and CO2 are great radiators. So this energy budget, if you like, is controlled to some extent by what you've got here. And in fact, the kind of search for climate change involved looking in the thermosphere to see if, as we put more CO2, methane at higher altitudes, which are IR radiators and hence coolers, does that show a cooling in the upper atmosphere above this layer? And there have been papers and studies showing in some places evidence said yes, and unfortunately in other places the evidence wasn't so clear. So we do know how important this is as well. Okay. So now I got here just a diagram. I'm going to ask you a question. Would someone like to describe the purpose of this slide? Everything we've talked about, just about, is based on being able to do this what we're going to do. Does anybody know what we're talking about here? Ionization rates, but what's the purpose of the diagram? Right, and what's that based on? Latitude, what else? Look, yeah, the Earth rotates. So this is, Sidney Chapman is kind of famous for what's called the Chapman Layer. And this is basically what it is. It captures the two other things we didn't talk about. Everything we talked about up until now is basically noon with the sun exactly above you. But that doesn't last for very long. The Earth rotates under you, and if you're at different latitudes with different seasons, mathematically the ionization is modified. So if you go to the terminators, the dusk or the dawn, this angle goes down to almost 90 degrees, but there is still some residual ionization. In fact, you can go about almost 10 degrees beyond what you call day-night boundary and still have some ionization at these higher altitudes. So this then, from Sidney Chapman, leads to these things called Chapman production rates. I've called this a wicked plot because everything's normalized. You don't have a useful number. We have the production compared to noon vertical as 1. And then, of course, the height where this occurs is not specified either. It's just relative to a scale height, and then is for the maximum is at noon. So this diagram does show you one very important thing. The height of the layer at noon, where the light is coming straight down, is at some altitude, which of course isn't specified here. But what happens at dawn and dusk to where that peak is? So at dawn and dusk, the peak is much higher. Now this then, in terms of trying to understand how simple this process is, it's just an optical depth problem. Sunlight which comes straight down on your top of your head goes through a certain density of gas. The light that's going tangential is passing through a lot more gas before it gets down to that particular height. So the height at which most of the ionization occurs is at a much higher height. Now, this might suggest it's a hugely different height. It's only about 10 kilometers, 5 to 10 kilometers. Yes, sir? Mm-hmm. The answer should be yes, but it depends on the spectrum, okay? So if the spectrum is the same from the stars, integrate up, is the same as from the sun, it's just a question of the optical depth, how much material you've gone through. So you should generate the same kind of distribution. But Lyman alpha, which is then preferentially resonantly scattered from hydrogen, it then forms a larger component. But Lyman alpha's profile isn't this profile. It penetrates somewhat deeper and requires things like NO to be the gas that it's ionizing. So there are complications, but the answer is primarily yes. Okay, so this then summarizes, if you like, what we know and what we observe, and it's completely consistent with the discussion that we've had. We've got temperature versus height. And this is obtained from an incoherent scatter radar system at Millstone Hill. So the one is at 1422 local time, which is 2 o'clock in the afternoon. And the other panel is in the middle of the night at 2 o'clock at night. So in this example, there's no sunlight directly. And this example is driven by our sunlight. And what we've said is we've got a neutral temperature, as we've talked about from the very beginning. This neutral temperature is sitting about 1,000 Kelvin. It's gone constant. And I've got the question I'll ask in a second. And then the ions kind of lock on to the neutrals low down, are in the same temperature range. And the electrons then are hotter. And this comes back to photoionization, leads to photoelectrons which have EVs of energy and have to thermalize. So the electron gas in these processes is always warmer. In addition, of course, high up, it depends on whether you're at the equator with a particular field line geometry or at the polar regions where the other end of the field line links. So if it links into the magnetosphere, you can have a hot source up there. But this is at Millstone Hill, so we're pretty much at mid-latitudes. And this would just be a normal, the photoelectron transport from one hemisphere to the other. At night, things are colder for the electrons. But you can see from day to night, they've changed the scale on us. This starts at 200, this one at 400. So the scales have changed just a little. But basically the day-night variation down here is, as we expected, negligible. Up here, going from day to night, there's a small cooling, if you like, for that neutral temperature. So here's our question. What does the exospheric temperature refer to? You'll find in textbooks and others that when we talk about the neutral gas above this region that we're kind of leading towards describing, we refer to the neutrals as being at the exospheric temperature. Okay, so what am I referring to when I say the exospheric temperature? Okay, so the first thing is the exospheric temperature is the neutral. It's the neutrals. It's not the ions. It's not the plasma temperature. It's the fact that once the neutral gas has gone through this heating region, if you like, above this, the temperature now is constant. And whether it's 300 or 400, at some altitude, if you measure the neutral gas temperature, you can be assured that the neutrals above you are at the same temperature. And this is a way of characterizing the thermosphere. It's at the exospheric temperature. Oh, question, good. That's right, you're just about decoupled, not completely yet. But of course, all of our models still regard it as collisional. And this, of course, is a little problem that we kind of have in the ionosphere too. As you go higher up, it's no longer collision dominated. And as you get into the magnetosphere, the problem becomes even tougher. But we still regard it as collisional. So you're right. In reality, there's structure there. Okay, so this is kind of where we're headed. This is the solar EUV and X-ray energy deposition. So now, I'm not talking about the ionization. I'm saying that you've got energy pouring into the upper atmosphere. Where is that energy dumped? Okay, and this is during, if you might call, just quiescent, normal, quiet sun daytime. And this ugly curve is where that energy is deposited. It's in two parts. This is the standard EUV, which you'd argue might be 10 nanometers up to 120 nanometers. The absorption of this energy into the atmosphere is primarily through ionization. It's the main mechanism. And that's about 150 kilometers. This is the energy, if you like, that created that thermospheric dependence on the solar cycle. Up there, this energy heats up the neutrals, and the energy can flow upwards, if you like, or the neutrals, the scale height changes, and the density above you and the temperature is changed. The energy flow isn't downwards because the density is ever increasing, and even if you had equal amounts flowing up or down, the impact on flowing downwards is negligible compared to the local energy that's there already. So the EUV is controlling the kind of normal solar cycle dependence that we know about. And underneath this, there's another sharp layer. And as we go into the second part of the talk, this becomes more important. This is the soft X-rays, the 1 or 2 nanometers to about 10 nanometers, and Lyman alpha. So under quiet conditions, your Lyman alpha at 120-ish nanometers is also responsible for this peak. So this is where all that energy goes. Very little energy from the solar spectrum at these wavelengths. EUV and X-ray goes lower. Of course, the solar constant, our optical, goes all the way down, generating our stable atmosphere. Okay, so why do the X-rays penetrate deeper into the atmosphere than the EUV? Why is that? And it's so tempting to say that. That's not the answer I want. I know the photons are more energetic, but what's the reason that they get deeper? Plasma physics? No, it's simpler. Motion of, no? No? It's a cross-sectional problem. Your cross-sections are not just temperature dependent, but different wavelengths, different cross-sections. And it turns out the cross-sections are quite different. Why isn't optical visible white light trapped up here? because the cross sections is so small, they just come all the way down. This ionospheric generation is nothing other than an optical depth problem. You go only so many kilograms of matter before you're guaranteed to be absorbed, or you ionize something and get absorbed. So everything we've talked about, these depths and everything, are simply due to cross sections, at different wavelengths. If the planet has no significant magnetic field, hence devoid of a magnetosphere, the atmosphere with photoionization is the physics needed to generate the ionosphere. So that would be the end of the story. But we on Earth are lucky and have a magnetosphere. Hence, we get even more physics to complicate our ionosphere. And that's what we're about to go to. But since you've been a good audience, we can have a break. Who wants a break? 2 minutes, 5 minutes? Let's go and have a break. Okay?
Statement regarding the cross sections. Aren't the cross sections themselves decided by the incident energy, or like the frequency that the?
That's right. The cross. If you take N2 and say what's its cross section, it's not a single cross section. It's a function of the wavelength or the energy. And then on top of that, at any given point on that curve, if you pick a cross section, it's got a temperature dependence.
Yes.
So yes.
So I mean, so that will also have to be chemistry dependent then, because I mean, your X-ray will it affect, like say, all the particles equally, all population, all density populations equally as.
Well, no. It gets complicated because for every species that you've got, you have a different wavelength cross section.
Yes, exactly.
So that's right. So then that's in there, and then you have to the best of our knowledge, put in the temperature dependence. And a lot of this work was done in the 1920s for medical purposes, as people were learning about treating cancers with radiation. So that they had alpha particles, beta particles, and electrons, and they had to find out what the penetration depths were.
Radiation poisoning.
Right. Yeah. Or if you wanted to, remove cancer or attack cancer, you had to turn on wavelengths that you kind of understood how far in it was going to go. So they kind of, we have this thing called 34 electron volts is the amount of energy you need for a further ionization by an electron. That's all going back to the medical studies that were done with beams of electrons and looking at ionization rates and things. So creating an ionosphere with photons is complicated, but it's still very understandable, right? It's just and that's now the same for all of our planets and exoplanets.
Plus, I mean, your radiation intensity will also, should it change with distance? I mean, farther out.
I mean,
your spectrum will definitely change.
But photons are going to just fall off as a 1 over r squared. And that's definitely going to happen. Venus is closer in, but Venus has a denser atmosphere in some way. So it's the temperature that determines how deep you go, right? Because you're basically arguing you have to go through so many grams of the gas before you're not going to get any further. And that's kind of where we're headed. Okay.
Thank you so much.
Okay. Okay. Oh, yeah. Okay, let's start again. Okay, let's kind of begin again. So from the questions I received from a few of you, I got the message that you're understanding this, which is brilliant. The physics of this first part is fairly standard optical depth physics. Okay, so this next part, the Earth and some other planets have intrinsic magnetic fields. And of course, during last week, you heard lots about magnetospheres and things like that, including some of the lab work was with magnetospheric models and things. This in the solar wind leads to a magnetosphere with its magnetopause boundary. Okay, so that's great. Now, if I talk about what's the purpose of a magnetosphere? You know, you might argue it shields you from really bad energetic stuff, but I could turn it around another way from the ionosphere. Simply put, MHD and magnetic reconnection physics provides a means of energy to be extracted from solar wind structures such as CME, CIRs, etc., and leads to an internal energy flow, a fraction of which is deposited in the upper atmosphere. So coming from my ionospheric point of view, all that physics with a magnetosphere, big deal. It's just a huge, big cross-section that's absorbing energy and dumping it where it should go, okay? So if you take that perspective, we can move forward, okay? The two primary mechanisms for getting it down to 100 and 120 kilometers are auroral precipitation, which is another form of ionization, and then the divergence of Poynting flux. We heard a nice 5-minute pitch on Poynting flux earlier on. And Poynting flux is the primary. If I take a geomagnetic storm and compare an X-ray flare energy deposition, the auroral deposition, and then introduce Joule heating via Poynting flux, it's always the Poynting flux Joule heating that's the larger component to bringing energy into the upper atmosphere. So there's 3 processes now. We've got solar flares associated with solar activity, and auroral precipitation and Joule heating. So what we'll do is we'll just start getting into this a little bit. We'll start with auroral ionization. So, okay, magnetosphere generates ionization via energetic particles, usually electrons. Now, I picked electrons, but there are a proton aurora, so it's not just electron aurora. You do get ions being heated coming down fail lines. There are different types of aurora at more like mid-latitudes. We got SAR arcs, very red, very low energy electrons. But what we're going to talk about are the ones that form the main auroral regions, okay? And the kind of manifestations. These particles are energized in the magnetosphere and create ionization and heating in the thermosphere, ionosphere. So we're back to the same region. Auroral displays are the manifestation of this process, and then ionospheric conductivity is a dynamic resistor in the MI electrodynamic system. Okay, so what we mean by that is MHD systems have variations in magnetic field, alphane waves, currents flowing, and these currents have to close. There's generators, and then there's places where there's energy deposition. And the resistor is this thing in the ionosphere we call Holland-Pedersen conductivity. And that was the thing we talked about earlier on. Okay, what's really special about our aurora, now, if we do exoplanets and different magnetospheres, the question could be that what's true here on Earth might not be true there. And what I mean by that is, if I look at what auroral electrons do, electrons come from above the atmosphere, just like the photons, and penetrate downwards. And again, they're going to go through matter, the neutral gas, and eventually get absorbed through ionization. Okay, so it's the same process, only you start with electrons and not a photon. Because they're in space, in the magnetosphere, the magnetic field line controls their dynamics. And then you've got things like E cross B drifting and whatnot. But these are energetic electrons. But they're not really energetic. They go from a few kilo electron volts to maybe 10 or 20 kilo electron volts for the main aurora. Now, there are MEV particles in the ring currents and radiation belts and other places, but that's not what we're talking about. These are the ones which, when you see, how many of you have seen the aurora? So why haven't the rest of you seen aurora? Okay, that's, yeah. Okay, so forget that. We'll come back to that one later. Okay, so the aurora is produced primarily by electrons in the 3 to 8 keV range. So as they come down, what you're looking at is the ionization rates for these 6 different model studies here that's showing you where the absorption through the ionization process occurs. And of course, that's kind of where these electrons dump their energy. So the question might be, at what altitudes do these 3 to 8 keV auroral electrons produce most of their ionization, i.e. dump most of their heat? And where is that? Ah, good. Thank you, sir. You're getting there. Okay, so for our Earth, it's true that the aurora is dumping its energy, creating its ionization in the same place as the solar flare X-rays would be dumping it, okay? And the process is, once they create, you get all of the chemistry we've talked about, you got heating and other things going on. So the second part then is, we've now got ionization enhanced in this belt, And of course, the enhanced ionization in a neutral gas through collisions leads to this process, represented by conductivities, the Hall and the Pedersen conductivity. So in this plot, which is kind of complicated, what we're looking at is the region of primary interest down here. So there's nighttime curves, and then there's daytime curves. And the Hall, the little H and the P, the Hall and the Pedersen are down here. The Pedersen layer is always a little higher than the Hall. But the Hall and Pedersen peak in this region. If you have a stronger aurora or an X-ray flare, it's in this region that the ionization is dramatically enhanced. At night, as we've said, there is still some residual ionization due to resonantly scattered radiation and starlight and things. And of course, aurora occur at night, so you can actually get enhancements there. And at night, this is a quiescent night, but under auroral conditions, you can get significantly larger kind of conductivities. Okay, so from an MHD point of view, from a plasma physics point of view, the importance of this layer is through the conductivities. So if we now have currents flowing into this system, electric fields, this is the layer with the largest conductivities where the energy, this Poynting flux, then leads to what we call Joule heating, frictional heating, that the energy is deposited during storms. Okay, so magnetospheric electric fields. In the F region, the electric field, I've put the neutral winds. A student did mention about neutral winds. The neutral winds exist lower down, but then above this region, there are other very strong winds that are kind of driven by the interaction of E cross B moving ions collisionally in a gas that kind of picks up the gas and starts moving it. And that can be quite a significant driver too, but I've made it smaller letters that we're not going to talk about this significantly today. So anyway, you've got the electric field, and although I've said that the Joule heating is the big term I was interested in, it's kind of important that an electric field in the ionosphere does other things. And we heard from one of the talks this morning, at low latitude, equatorial latitude is a very important thing, the low latitude electric field. And then, of course, there's the high latitude electric field. Anyway, the purpose now is plasma physics. We said that the F layer has a very strong diffusion control at the upper part and lower down its chemistry. Well, the diffusion balance can be interfered with by introducing winds that push the plasma up or down field lines. So anyway, that's kind of important. And then we said that Joule heating depends on the Pedersen and the square of the electric field. This is just a formula. But at all latitudes, E cross B can transport plasma perpendicular magnetic fields. And that's up in the F region. So what we're going to do now is just give you an idea of what we mean by this E cross B drifting. What kind of things can happen. Okay, okay, so I think I've beaten this to death. Does anybody not know the answer? Put your hand up. So there are no hands going up, so you all know the answer. Okay. Okay, we'll come back to that. Don't worry. I'm sorry the colors haven't done too well here. Okay, so we're at the equatorward. So we're equatorward winds at mid-latitudes. So it's not at the equator, it's equator winds at mid-latitudes with inclined magnetic fields. Why are the magnetic fields inclined at mid-latitudes? They're not perpendicular, not horizontal. What are you thinking about? What's the geometry you're referring to for the magnetic field of the Earth at mid-latitudes? How do you represent the Earth's magnetic field close to the Earth in the upper atmosphere? It's just thank you, sir. It's just a dipole. At the equator, which direction are the magnetic fields? Horizontal, yes. And at the pole? Vertical. Yeah, and then that's the topology that you've got to be thinking about. So when I say mid-latitudes, my field line's inclined. And the question is, what can a wind do to the plasma, okay? So here's a wind blowing, and the wind it's a neutral gas that's now moving, and of course the neutral gas through collisions is expected to move the plasma as well. But why is the plasma attached to the magnetic field? What's the process that ties the plasma to the magnetic field? Yeah, it's free to gyrate, but not free unless it's E cross B drifted or something. So what happens when a wind pushes from right to left plasma on a field line that's shaped like this, tilted like this? Where's the residual component of the wind's effect? It's almost like sliding it up the field line. So this would produce a lifting of the plasma, and this goes into the diffusion equation and leads to the plasma layer being raised. If the wind was blowing the other way, the residual component that's consistent with the gyration physics is to drive it downwards. Okay? If you drive it upwards, you're driving it into a lower density region. The recombination rates are less, so the plasma lasts longer. If you drive it downwards into a more dense region, the reactions go faster and your recombination rate goes faster. The plasma lives less time. Same for an electric field, an E cross B electric field. The E field is coming straight out at you, so it's a horizontal electric field, and the E cross B wants to drive it perpendicular. But again, for the same reasons, what you have is a lifting of the kind of layer. So this is all part of the diffusion equation. You've introduced a component that competes with gravity acting downwards. Okay, so that's one pretty important reason for electric fields and winds. And we just talked about this. So I've answered the question before I should check to see if you've got the question right. Go ahead. You have a question? Oh, okay. So what we want is in the diffusion equation, the diffusion equation, we normally cast it as a vertical. So we have to transform, if you like, all components into the vertical. So this thing called U2 is the component which goes into a computer model where it's regarding the motion, the diffusion motion, straight up and down. Yeah. So the component is the E cross B is broken up into two components. There's a plasma component horizontal, but there's one that's vertical, and it's that vertical one which is effective in changing where the layer is. Yeah. Okay, so coming back to the equator, there is, as our student was telling us about this morning, at the equator there's an electrojet, was the emphasis he gave, but there's a very strong electric field as well. It's an eastward electric field, and that eastward electric field in the daytime actually causes all these little arrows. Okay, so this diagram, what you're looking at is the curved lines are supposedly magnetic field lines, and the equator is here, and here's our altitude scale. And basically in the F region, this E cross B, purely at the equator, leads to this vertical drift. But as you go away from the equator, the drift is kind of like this. So these components of velocity for the ions, if you like, lead to not just a straight up and down ionosphere. They go into the diffusion equation, and plasma transport becomes important. And what you end up with is what's called the equatorial anomalies, or the original name was an Appleton anomaly. Basically, if you look at this plot from here's equator, and as you go north and south in degrees, this is to the southern hemisphere and northern hemisphere, the ionosphere isn't this nice layer at a fixed height. What you have is altitude, and these are contours of log 10 electron density, and the units we still tend to use are centimeters cubed, per centimeter cubed. But this is 10 to the power 6 or thereabove, 10 to the power 6 and above. And at the equator itself, there's almost a minimum in the peak. So now when we talked about the peak in the F region was about 300, And at the equator, you might argue it starts at 450 as you go towards the equator. So you're coming from the southern hemisphere, 24 degrees. As you move in latitude towards the equator, the F layer is rising. It rises up to 600 kilometers in this example. And then in the other hemisphere, it starts to fall back down again to somewhere like 300. So this kind of ionosphere, if you like, come back to GPS. If you're sitting on the ground, which would be somewhere, and your GPS satellites are in different locations, this thing, the analysis your algorithms want to do to compensate for the retardation in the radio waves is kind of complicated. If you had a path through here, you have one set of density models that you would need. This one's a different density model. So the models in the GPS receivers have to start to build in these kind of structures. And of course, this is not frozen. Day and night, it's changing. Our student is trying to understand these electric fields that cause this problem. And they're very variable. During the storm, the plot he showed, the vertical drift that leads to this changes by factors of 3. So it's kind of important. So that's the electric field at low latitudes. However, if you go to high latitudes, the electric field is different. It's now connected to the magnetosphere. And the magnetosphere has what we call a cross-tail potential. The dynamo or the generator generates this huge electric field that maps down into the high latitudes. So that what you have is the polar plot, midnight, 1800 hours, noon. The magnetic pole would be centered. And there's two lines with arrows, and we'll come back to them in a second. But initially, you'll notice there's lines that form circuits, if you like, closed convection lines. These represent E cross B. And high latitudes, the magnetic field is vertical. You've got horizontal electric field, and you get E cross B drift in the plasma. And from noon, it tends to be anti-sunward in the polar region. So this circle, if you like, this is a model, so it's not meant to be reality. But this is supposed to map out into the magnetopause in the tail in some way. The cusp would be up here in this region. And then at mid-latitudes, an auroral region sits around here. So what you can see already is, from an experimental point of view, the Satellite Dynamics Explorer 2 was measuring the drift, the plasma drift. And of course, this is a perfect fit. As you see, the plasma flows sunward outside the polar cap. Inside the polar cap, it flows anti-sunward. And then again, on the morning side, you have the same again. So of course, this is a kind of mishmashed, put together perfect case that never happened. Okay, we've got a perfect convection pattern. But these electric fields now are important. Okay, so if we go a storm scenario, okay, so we'll step back for a second. The TEC, what does TEC stand for? Total electron content. So that's this integration through the entire ionosphere to get, and actually beyond, out to the satellites, if you like, the GPS satellites. The kind of knowledge that we've had in the last 20 years has come because all of a sudden you can have multiple sensors all over the ground. The oceans are still harder, but we get great coverage with multiple sensors. So we have TEC from all over a region like this. So this is an observationally based kind of inversion, if you like. Well, of course, we recognize the United States and Canada, Hudson Bay. Basically, what we're plotting here is the total electron content under quiet conditions. And it goes from 0, which it rarely gets to, up to 120, and that would be in tech units. So this is a quiet day, kind of around noon. What you have is higher densities lower down, mid-latitudes are moderate density, and if there's no significant aurora, the polar regions are kind of much lower TEC. So there's nothing weird there. But the next day, this was a big storm in 2001. The 30th of March was the quiet day. The next day, a phenomenal storm occurred. People here in Boulder, in Utah, and Texas saw Aurora. So, how many have not seen Aurora? You guys will get fed up with me pretty soon. The kind of phenomena then, all of these electric fields we're talking about are moving plasma like nothing. The Joule heating is going on, raising the temperature. As the temperature of the neutral gas goes up, the recombination rates increase, the plasma density diminishes. And what we're looking at here is how complicated the ionosphere suddenly becomes. The density throughout mid-latitudes decreases slightly after the main storm, and this is called the negative phase. But from a GPS point of view, this difference isn't just a few percent. It's kind of going from down here tens of tech units from what was 60 or 70. The GPS corrections, in fact, during this time, many of the airline systems, the wide area augmentation system, failed for half a day or so. Okay, so the plasma density diminishes, but it doesn't everywhere. The electric fields are kind of complicated, and here's a ridge of very high density leading up to the polar regions. In fact, we're not going to talk about it, but this enters the cusp region, produces patches, tongues of ionization, and other phenomena. But the electric field, the new pattern during big storms, leads to effects like this in addition to the heating that we talked about for Joule heating. Okay, just to kind of give you a heads up on when we say the heating increases the recombination rates and the plasma density decreases. Here's kind of how that works. Here's the perpendicular electric field. That's what we're referring to. There's not an electric field along the field line. It's perpendicular. It's zero. And this would be our conventional ionospheric structure. Here's the electrons. There's two kind of regions. There's the lower down region, and then there's a higher region called the F layer. So you've got this TEC if you integrate this up. And this is O+, nitric oxide plus, and O2+. So the molecular ions low down and O. So you're getting the hang. Now, crank on an electric field at 100 millivolts per meter. This is not abnormally high for the polar regions. It might be plasma flowing at 2 to 3 kilometers per second horizontally. Well, O+, it's disappeared. O+ has gone from this to this, and this would be in tens of minutes or less. And what's happened is the first step is that the O+ recombination rate, it's not so much the recombination rate, but it's the conversion rate to NO+, the chemistry that occurs. That when you heat up the gas, the NO+ enhances and the O+ decreases. But of course, as the NO+ goes lower down, its actual recombination rate is sped up too because it's colliding more effectively with more neutrals. So in actual fact, the overall picture is that down here, the E region isn't perhaps changing dramatically, but the F region is all but gutted out, which means the TECs have changed, and these TECs from 60 down to 10 is kind of relatively easily explained with simple temperature-dependent physics as heat gets put into these things. And our GPS, I always come back to GPS, this is what's affecting your GPS. Okay. So how we ionospheric physics over the years have kind of worked. The morphology is a systems level problem, but we've always tried to go into different latitude regions and try to understand what's going on in that region and try to get a complete picture. But historically, our early models tried to just simply, if I knew how the equator was working and how the high latitudes, I just pieced together these density models. And that turns out not to work very well. Not a good approach. One has to, in modeling, just like one liked to do with the sun and the solar wind, do a complete end-to-end at all possible time scales, at all possible spatial scales with all the mechanisms. And we're kind of far from that even in our ionosphere thermosphere, although we have very good coupled models. So it's not a linear superposition of densities, to put it simply. Okay, so we're at the point at which we do try to put system-wide processes into the models. So this is maybe an elegant simplification. You've got auroral precipitation, joule dissipation, solar EUV, plasmaspheric downflow that we haven't talked about, starlight and scattered radiation that we have. So this group, and someone already threw in meteors. I don't want them, but thank you. So we've got them. We've got UV radiation, X-rays. This is the kind of DE region kind of crossover, and very energetic particles. I should say that there are extremely energetic particles, but from the point of view of an ionosphere thermosphere, the energy content where they get absorbed, their energy deposition is totally negligible compared to that lower atmosphere, very high density. So they don't have a thermal impact. Although energetic particles can kill satellites. If you're flying across the polar regions during one of these events, it's not a healthy place to be. So I've excluded energetic particles, but they are also very important. And as we just talked about, and we've seen an example, from below, stuff is coming up too, tides and gravity waves, the dynamics. So that's what you'd like to do, but then you kind of look at it pictorially, and you give up. Okay, you know, you take a look at this and you say, it's not for me, right? You know, now fortunately I've gone through my career. You guys are faced with this. You know, we've cherry-picked our careers, our dissertations, where I could fly a rocket into the Aurora and measure something no one else had measured before. That's getting harder and harder. You guys are being forced to work much harder than I ever had to. So I'm kind of encouraging you. But so there you can see the two cells, you know, the kind of electric field uniform across the polar cap. The sun's over here, plasma moves. Then there's an auroral ionosphere. We most certainly have things going up and down, and these things going up and down are electrical currents from the magnetosphere delivering energy and other things. Then you've got all sorts of things, words like gravity waves, tides-driven things. Anyway, the modern day ionospheric, thermospheric, atmospheric model, let alone coupled to the magnetosphere, includes all of this stuff. Okay, so this is a better summary. When we talk about energetics, where is the energy coming from? What process is the dominant one? So historically, we kind of deal with them as separate things, or we try to. But in actual fact, it's all one energy flow from this magnetospheric energy. Typically, during a big storm, we're talking about 500 to 1,000, I think maybe a little bit more, gigawatts. That's the kind of energy, you know, joules per second that's flowing in during a geomagnetic storm, a big one, into the ionosphere. Now, there's more energy in the magnetosphere, but it doesn't all get funneled down to the ionosphere. Okay, less than 20% goes into the auroral stuff, and that leads to heating, it leads to the air glow, auroral illumination. Then the other part is what we call electromagnetic energy. So the divergence of the Poynting flux as it approaches the upper atmosphere is what we're talking about. The part that I've mentioned mostly is the joule heating. And of that 80%, the bulk of it, I'm not so sure necessarily agree with these rounded off numbers, but it's mainly joule heating that ends up in this layer that we've talked about where the conductivities are high. That's where the energy is being dumped. There's heat, there's pressure, gradients. And when we get onto the second talk this afternoon, there's a couple other aspects that we'll bring up that are really important for exoplanets and things. But the other part is this kinetic energy. As the ions are being driven at 3 kilometers per second by the E cross B, they're interacting, of course, collisionally with the neutrals. So the neutrals start to pick this kind of motion up at high latitudes. And the neutrals then, it's just this gas is now flowing. So there is, in a reference frame situation, energy in that neutral gas that wasn't there before. And that's where this other 20% is. The interesting thing about this is, so now you've got this neutral gas moving. And all of a sudden the aurora stops or the storm subsides. Well, this switches off almost immediately. The electric fields die immediately. But you've got this huge reservoir of energy in the neutral gas now flowing. And this then is referred to as the neutral flywheel effect, where you've kind of pumped in energy and got this neutral gas just flowing. And after the storm, this energy takes a lot longer to subside. Okay, so we've got a couple examples. We're still good. The coordinate system is even worse here. It's local time along the bottom, going from kind of midnight to about, sorry, if I can't read it, how can you read it? It's supposed to be noon towards the center, sorry, and then going late afternoon over here. So this is near noon, 2209. And then this is latitude, the equator here, northern hemisphere, southern hemisphere. And this is from a coupled thermosphere ionosphere model. And what they're looking at is the effect of a big storm through Joule heating on the thermosphere. And what's really important is the colors. The colors here represent temperature. So the blues and purples are about 1,000 or slightly less. So this is 1,000 degrees Kelvin in the F region, so exospheric temperature. And I know this is a little bit, in the late afternoon, a little bit higher, and depending on the season, this is slightly warmer, if you like. But it's still around 1,000 to 1,200. You get a large geomagnetic storm, and this Joule heating, it's not just at high latitudes where you expect the aurora to be, but it's propagated globally. So the dynamics of this gas redistributes the energy globally. So all of a sudden, after the storm sets in, it's a big one that they've put in here, we're up to 2,000 degrees Kelvin. So the temperature's doubled. And that doubling has occurred in something like 6 to 8 hours. It's true that at the high latitudes, you do get a preferentially even hotter gas where the direct heating is going. But the important thing is, when you put that much energy in, neutral dynamics changes. Instead of being, an equilibrium hydrostatic kind of problem, it's become a very non-hydrostatic, and waves are set up and launched towards the equator into these regions of lower density, lower pressure, if you like. So the dynamics is really profound and on a global scale. So it comes back to this word global scale. Observationally, we can't actually measure many of these important parameters. So here is an example from the CHAMP satellite. You're at 400 kilometers. This satellite was very specially designed to detect small changes in density, among a few other parameters. So what we've got here, at this particular day 8, January 2005, there was a very well-defined geomagnetic storm. And we'll talk about each one of these in a second. But the bottom line was the density, the neutral density the satellite experienced went up by a factor of 2. So the drag on the satellite was very measurable. And the source of the energy was the interesting thing in this study. So the first part here is the hemispherical power from auroral particles. It's 200 gigawatts was the kind of power from the auroral point of view. The Joule heating in the two hemispheres measured was actually, here's 200, and this got up to 800. So this dominance of Joule heating is fairly well established observationally. In the southern hemisphere, it's a little bit higher. And then the kinetic energy, this energy of getting the whole neutral gas into big circulation, gigawatts-wise, it's quite small. It's only 20. So that's kind of my reason for poo-pooing this kinetic driving, if you like. And then finally, in addition to all the heating terms, there is the cooling term. And we mentioned earlier, if you had nitric oxide, methane, carbon dioxide. These are extremely good radiators. And what you have is, at the peak of this storm, 120 gigawatts, which is kind of in the ballpark of these things. And what you'll notice now, if you look carefully, the geomagnetic inputs eventually cut off, but the cooling goes on for several more days, a couple of days. And that's kind of how the process comes back to equilibrium. It takes several days after a major storm input. And it's not just through NO cooling, but that's an example. Okay. And this storm occurred on January 2005. Okay. So this is us going to kind of summarize a little bit, but I want to introduce one more complication. So the geomagnetic storms are part of the space weather, because the next talk this afternoon is more on the space weather. How bad can it get and what can it all do? Solar flares are part of that, and we haven't really talked about this. But both of them end up depositing their energy at 100 to 120 kilometers. As a consequence, the atmosphere above in what's called the low Earth orbit region is kind of modified. And there is this one really nice example. This time it's from that Chapman satellite again, which measures the density. And here we have latitude going equatorward here, northern hemisphere, southern hemisphere. We're at 400 kilometers, and it's several days. This black trace represents the X-ray flare that occurred. And the GOES satellite has two different channels that measures the X-ray flare intensity. So the period is flaring in general, but there is this very intense X-class flare. When the X-class flare came in, almost immediately you can see the density at 400 kilometers went up. So this is just evidence, very clear, that the ionization occurs down at 100 kilometers for the X-rays, but the thermal energy that's being deposited is sufficient that the neutral gas is heated up and the densities change and there's dynamics. And for several days now, before the thing can recover, the satellite experiences significant drag. Okay. So just wrapping up, I've got, I think, 3 more slides. We're good. So now I want to just emphasize during an X-class flare what happens. The ionization occurs where we've said 100, 120 kilometers. The energy deposition, which is what I'm plotting here, occurs in this layer. And the heating is above, but there's almost no impact below. So this layer, if you like, protects the lower atmosphere, and the upper one, of course, becomes turbulent. The temperature doubled for the examples that we've seen. So that's what happens on the Earth. And we know enough that we can do this too for the CO-dominated Venus and Mars. The same kind of flare, I kind of drove through the Martian and the Venus ionosphere. And both of them form layers. They form at different heights because the density structure of the two aren't quite the same. But they form a narrow layer. And the same arguments will happen here. Below it, the atmosphere is protected. Above, it gets heated. Okay? And of course, it's not a surprise. Oops. You can go to Jupiter and Saturn, and technically, the same thing happens. The response to that flare is a layer. Blue is Jupiter and red is Saturn. Most certainly, the altitudes are different, but that's not a surprise to you. Once you know something about a planet, its atmosphere, these calculations are pretty straightforward. Basically, the energy deposition is occurring at some altitude. Above is at risk to the space weather. Below is at least protected. And this is then, space weather has several important mechanisms that coexist between 100 and 120 kilometers in the Earth's atmosphere, ionosphere. So this is our takeaway from this morning. So we're going to introduce now what the word SARE, or the acronym SARE, meant. So the Sun-atmosphere interaction region is one way of looking at it. But you can also regard it as a space-atmosphere interaction region. And eventually this afternoon, we're going to treat it as the star-atmosphere interaction region. So as we get into exoplanets, know something about their atmospheres, we can most certainly readily understand how the ionosphere, this region that we're talking about, this band, protects a lower atmosphere from a higher one. The kind of little extra bit of information is, what do we mean by protect? Once you heat the gas above this layer, there is a thing called kind of Jane's escape, where you energize the molecules or atoms sufficiently that they're free to escape. Below, of course, the atmosphere is still cold, so it's not being affected. But nonetheless, the layer is where you're raising the gas temperature and blowing it off if you get high enough. Now, fortunately for our Earth, that doesn't happen. That this isn't a mechanism for losing the atmosphere. Okay, it's lunchtime. That's enough of the good stuff. We'll get exoplanets later.